Everyone, this is the Ethereum developer course. My name is Gabi. I'm gonna be leading this initiative to share what I've been learning about Ethereum in the past couple of years. And this is my idea with this course is to share with you a practical lectures of how to use Ethereum and Ethereum technology in practice and how to leverage existing developer technologies that are available for us. And these are several toolings that are been evolving in the last year or so that are really, really powerful and really, really important to understand to have a better developer experience when we are dealing with Ethereum. And to give a bit of context of myself, I'm Gabi. I've been in the One Hype community for almost day one, and I've been learning all this developer stuff on my shop in Aragon and participating in the Aragon community mostly. And I had the chance to have a really good mentors that share with me a lot of the things that I'm gonna try to also share with you and try to build on their shoulders on stand on their shoulders and yeah, keep learning with you through this process. And yeah, to give a bit of context of the schedule, if you didn't see the blog post we discussed about, we are going to be in the week one, we are going to be today doing a Ethereum fundamentals overview. Then on the week two, we are going to scaffold an Ethereum project from scratch. In the week three, we are going to be using one of the most important toolings that is available for us, that is Hardhat, and going into in depth into the different moving pieces that provide us to be better developers. And yeah, week three, we are going to be using other really important tool that is Ether.js. This is a high-level tooling to interact with the blockchain. And we are going to use that tooling to write smart contract testings. Week five, we are going to be doing smart contract deployments on different networks and discuss a bit how that could be done in an efficient way. Week six, we are going to be doing a graph example and go through why it's important to use as a graph and why the graph exists and what is the value proposition that offers. And finally, on the last week, we are going to be bundling everything we have done until this day to put it in a simple React application and yeah, maybe have some nice interactions there. Next, for the course format, excuse me, we are going to be doing working groups, and the idea is to experiment a bit with this and see how we feel about it. The lectures are gonna be recorded asynchronous, and I'm gonna share it at the start of the week, and then also share a few materials and links that you can go more in depth into the topics that we are gonna discuss. And then the idea is that I also try to give a few tasks or exercises, or even you can come up with others exercise to do. But the idea is having these working groups as a way to share with your peers and learn and see other way of thinking about the topics. So yeah, really open to the feedback of and keep evolving on throughout the course. And at first we formed two groups. I'm not sure how many we are gonna be finally, but maybe it makes sense to have a couple of more groups or one more group. And but yeah, feel free to do what you are more inclined, even do a individual. Individually is not a requirement to be in the working group, but encouraged. And finally, I would like to show you a bit the Discord that I have created for this course. And the idea with the Discord is to have a place where we can have everything in one place. I will be doing the way that I structure so far and is having this section with resources where I will be putting the lectures, the materials, and the tasks. And these are only read-only channels. Then we have this questions and answers section one where I try to put all the topics we are gonna go through, so we can have a nice place to look the questions or answer really quick with the search. And then I have these three channels, more general for English, for Spanish, an introduction and a sharing group. And yeah, we will have these wide channels for working group sessions or pre-programming sessions that you would like to have. So yeah, that was the thing that I would like to cover. Now for the first lecture, I'm gonna start explaining a few of the fundamentals topics of Ethereum and also general blockchains at some point. And one of the tools that I'm gonna use for most of this lecture is this ETH-build tooling. It's a really cool tooling built by Austin Griffin, and I will link all the videos for you to learn more about it and go into more details of what it is. But this is a composable Legos for with a lot of the things of you can put inputs, you can put ways to display the information, storage, network connections, cryptography, Web3. So you will have all these different modules so that you can use and create really cool stuff and see to visually how some of the things behave in the Web3 ecosystem. So yeah, the first thing that I would like to show is the concept of a hash and a hash function. So we have this hash module that is doing that. It's showing us the hash functionality, the hash function functionality. So what we wanna do is input a text. So in this case, I'm gonna put Gabi here, and after I put it into the hash function, I will have a string of text return. And what is interesting is that if I change anything here, the hash function is gonna return a different value, and that's a property that we want to have for various reasons. And to showcase a bit better, let's put it a color to this for future. And we are gonna need a substring. So we're gonna take this string, and we only want the first two. We don't want it because these are the 0x is the usual way to display bytes in Ethereum, and in general for what it matters. And let's take only the first 6 values. So we're gonna take only this, and this is gonna be this color. So if every time I change something, the color also change. And what we can learn from this quick example is that the hash function is always returning a different value, and also that value is always the same. If I gonna do Gabi here, this is gonna be this color, and if then I put one height, it's gonna be this other color. But if I put Gabi again, the color is gonna be the same. So it's always a deterministic function is the technical name. So that's a really cool property. And the other interesting property that hash function has is that if we have this string of text or this color for what it matters, it's really difficult to know what is the actual input text that is producing that value. And that's also the second property that is really important for hash functions, because we want to obfuscate and protect what is going to be our input. So to keep building on this example, let's build a more complex structure. Let's take all this and let's put it into other. Let's replicate this a couple of times and okay. And what we want to do with this is reutilize the three hashes into and combine them into a new structure that is using the three of them. So we're gonna be taking the three. Oh, 1, 2, 3, and this value we are gonna also pass it to a hash function, and this is gonna produce a new string of text associated with the previous hashes. No, so now let's also take the color, so to make it even more easy to recognize. So given this, we are gonna put the string, and we're gonna have the color that is a combination of the three other colors. No, so what is interesting to notice is that if we modify whatever of these three texts, I don't know, if I here have Gabi 3, what is going to happen is that this color is going to change and this one is going to be affected as well. Maybe this is not show it so much, but let's keep changing, and what it's going to be is that this change is also reflected in this. And even if we go back to the initial, we're gonna be seeing the same, and the same is gonna happen if we go here and keep updating, and the color is gonna be different. The same. So, what is this example? What it's trying to show you is that we are creating a more complex structure here that have the property that anything that is changing into the whatever of the structure, the initial values, is gonna affect the final output or the final hash produced. And this is an interesting property that is used across the different data structures of the Ethereum blockchain. And it's important because allow us to reduce a lot the size of the things, and also keep the good property of being able to verify if something is what it's meant to be. So, okay, now building on this example, we are gonna be keep going a bit more into the other details. So let's start again with a text input, and let's use our hash function to produce a value. And this value we are gonna use it into a new module that is called keeper. And this keeper is asking for a private key. And this private key is like a secret that we want to store and we want to use eventually for different things. And in our simple case here, we are going to be using the same, the return of this hash as our private key. And we can use here the text as our our password. For example, I could be password, and here is returning us this hash, and we are using that as our private key. So then, once we have our private key, the keeper module doing a cryptographic function called elliptic curves is also able to generate a public key. And this public key is associated with this with my private key. And why is important our public key? Because this public key is something that we can share with others to identify us and do things eventually, but we are not revealing anything about our private key. And that's something really important that we want to accomplish to be able to build on the to do things in a secure manner. And what allowed this transition is, as I said, the elliptic curve cryptography. That is a complex math that ensure that this process is also a one-way function. So as we were saying with the hash, it's really difficult to do and almost now impossible to do from the public key derive the private key. Finally, we also have this other value, the address. And the address is what we usually are seeing when we are transfer an asset or we are interacting in Ethereum. This is the address that we are usually using. And to give a bit of context, how this address is generated is also doing a hash, but it's doing it from the public key. And this value that is returned, if we check the last 40 values are the same as this address. And that's the address of the Ethereum. The last 40 parameters, like here, the last 40 parameters of the hash of the public key. So before going forward, to review what we just did is giving a password in plain text that we are able to remember. And usually what you are going to see is several a more complex password, of course, but from a password, every time we have a different, here we are getting a different address, as you can see. And from here, we are using a hash to create a private key. And that private key is using the cryptography of the key pair to generate a public key with a really complex math called elliptic curves. And from the public key with another hash, we will get this string of text where the last 40 characters are the actual address that we are using in Ethereum, and that is the selection of using 40 characters is for improve the memory size in the storage. For what I know, the storage on the network, and keep it less, not so long, like 64 characters, if I'm not mistaken. And okay, now what we can do with this? Okay, this is what things are getting more interesting. And giving a private key, what we would like to eventually do is send some kind of message to the blockchain and make sure that we are able to assure others that we are the owners of this private key. So what we will do is use this other module called sign that is also using cryptography to create a signature using our private key. So what we will need is a private key, and we will gonna be inputting a message, or in this case, a simple text that say, I'm Gabi, and we are putting this message here. And then what this module is doing is returning a text that is our signature, that has our signature into this message. So what is happening here is that given our private key, we are digitally sign this message, this line of text, I'm Gabi, and generating this signature. And this signature has the property that eventually we can share this in the blockchain, and we can what it called broadcasting and put it into for others to see. And using other modules that we are gonna see now, being able to assure that we are who was the one that digitally signed that message, no? So then we are gonna introduce a new module called recover. And this recovery is also using cryptography to untangle this signature and being able to know who was the person that digitally signed it. So let's input to text to make it easier to see the message. We have it here, sorry. Yeah, the message and the signature. And what is going to happen now is that it's going to return us the address of the address that digitally signed this message with this signature. So as we can see, it's the same address of the owner of the private key. So what we just prove and realize is that using this technology and this cryptography functionality, we are able to be the owners of a private key, digitally sign a message, and create a signature that we can share with others to prove that we are the owners, or we are the ones that did this digitally, that digitally signed this message. And this property is really powerful and is the main concept that is used when we are interacting with the blockchain. As we are sending what is called transactions into the blockchain, we are actually digitally signed for a message that has a specific format that we will see is next, and we are able to prove that we are the ones, and that's what I wanted to say about that. And now, using all this functionality, we are gonna be creating our first transaction and send it to the blockchain. So let's remove all this. Let's keep with this only. And okay, what we are gonna be doing now is introducing a new value called balance to check what is the balance of this address in different networks. No, so what we need here is the address of that account, and let's put it here so we can see it. And we are gonna need also a blockchain. So what we can use here, okay, we can use networks that are available. We can use XDAI, we can use mainnet, we can use Rinkevi, but what we're gonna be doing is running our own local node. And for that, I set up this chain demo repo with Hardhat, the tooling that we are gonna learn in the next couple of lectures. And I'm gonna run a local network, a local chain in my computer. What is this gonna be doing is starting this local chain in this endpoint, and I'm gonna use that endpoint to feed here. So it will understand, and this balance module understand from where he needs to read this address. And as we can see, the value is gonna be 0 in this case. And let's put here a button to check the balance every time we want. And as we can see, this value is 0 because this address that we generate with this strange password is not initialized yet. So what we need to do is bring one of the values that Hard Hat initialized for us in this local network. And doing that, we are going to be introducing this other module called mnemonic. And what is this? This is an extra cryptographic module that allows us to set up a more complex key pairs or a more complex password for ourselves to use. So in this case, we are going to be using as our password the one that Hard Hat provides us. So let's put it here. This is going to be, and this is what is called the seed phrase. Yeah, sorry. Let me check if I have it right. Okay, here. Okay, I'm going to take it from Hard Hat to make sure it's the right one. Here, here is with the documentation, and in here they say this is the mnemonic that you can use to access all the addresses that are available with that we want. So let's put it here, our mnemonic, and what this is going to produce is a private key as we wanted. And here we can say, okay, I want the address number. I want the private key for the number 0, number 1, number 2, whatever we want, because this mnemonic is a more complex that allows us to have several private keys with the same password. So now that we have this private key, we can use it as an input here. And let's remove this. And what we are gonna see is that now the balance is really big, and that's because this account has already been initialized in the Hard Hat local network. And we can check, for example, here that if we go to the other address one, it's gonna have 1,000 ethers, 2, 3, whatever. Let's keep it in the address 0. And the other thing that I forgot to mention is this unit conversion is necessary to show in ethers. That is in ether. That is the main value of the unit. I mean of Ethereum. And this number that is really big is because it's expressed in a way that is the most small unit of account in Ethereum, and it's gonna be one with it's gonna be 18 decimals of value. So yeah, it's a really big number, but once we convert it to ether, it's gonna be expressed in ethers in this way. So yeah, now that we have an account that has a value, we can start trying to interact with this with the blockchain and try to send some transaction. So to continue, what we are gonna need is other module called transaction. And this module, as we can see, is gonna ask us for a blockchain once again. It's gonna ask us for the private key that it's gonna be using. And it's gonna be asking us a couple of more values that we would like to that. Let's go ahead and try to describe them. So here we will have the 2 that is gonna be where this transaction is gonna be sent. So in our case, let's try to send 1 ether to a new account. So let's put again our hash function. Let's create a new account from Gabi. So we will have a private key, and from this private key, let's create a key pair once again that will generate for us the address that we want. So in this case, it's gonna be this, the address, and this is the value that we want to put into 2. That is the address that we want to send some Ether with this transaction. So now in the value, we want to be sending, want to be sending, we're going to be sending 1 Ether, so 1. But as we remember, as we see in here, the units of account are in way. So we're going to be needing this other module that is 2-way instead to convert this unit of 1 Ether to way. So it's going to be expressed in the correct format. Then we are going to be data is not relevant for us now, and we're going to be discussing later. And gas limit and gas price, let's keep it as default and not give it too much importance now, at the same from the nonce. And with all this data that we just put it, this generates as this transaction object, and this is the information that we are gonna send to the blockchain. This is the message that we're gonna want to digitally sign to being able to propagate in the blockchain. And this is why the properties that we see in the previous example are going to be important, because this format of the transaction is the one that is going to be used. So if we check the signal, we need to, let's put a button as well to digitally sign this transaction with the private key of this address. So if we click here, we are going to be digitally signing this message and get it on this really big string. And let's put it here. This is the digitally signed text of this message, this transaction. And now that we have this information, what we would like to do is actually send it to the blockchain. So let's use another model called send transaction. And what we're gonna do is put the blockchain, and we are gonna put the blockchain here, and we're gonna okay, let's put first the signed message. We're gonna put the signed message here connected, and also the blockchain in the second value. Here. Okay. Oh, me estaba pidiendo. Un segundo. Le vamos a probar de más cerca si quiere. Okay. Okay. I put it. Then I was able to connect now. And what we would like to see is what is the hash of this and the receipt. So what is gonna happen once we send this transaction with the send button is it's gonna propagate this into our local blockchain, and it's gonna return us a hash that is associated with this transaction. That hash is gonna be the identification of the whole message that was signed for us. And it's going to return a receipt that has more information about the transaction that could be relevant. So let's go ahead and do that. Let's send this transaction and see what happened. And yeah, we were able to get the hash, so the transaction was created correctly, and we get the receipt that I was mentioning. And this receipt, let's try to see it more clearly. Yeah, it has a lot of values, and a lot of them are maybe zero. If we put it again, it's gonna detect that it's an object and put this other format. And as we can see, there has a lot of values. Some of them are the ones the same that we had previously in the transaction, but now we also have these other log bloom logs and other information like the gas that were used or whatever. But all this data is going to be relevant for us eventually when we are analyzing what happened with that transaction or what are the state that was updated in one contract, for example. But yeah, this is going to be more relevant once we look a bit more in detail what is the consequence of sending a transaction. Then the other thing that I can show you is that here in the local blockchain that we have, we can see that we send the transaction and we see here that a value of 1 Ether was sent. So what we can finally do is that make sure that this address now has a value. So let's put another balance here. Let's connect the blockchain to there, to here. Ouch. Let's check the address of this address. Put it here. Let's connect the blockchain as well. Okay, and now we can see that we have a value of 1, and of course 1 once we convert the weight value, and we can see that the state was updated correctly, and now this address has 1 Ether, so the transaction was successfully sent. And what is interesting and would like to remark once again is that with our private key, we were able to digitally sign this transaction message and send it to the blockchain to further process it. And now with this context of what a transaction is, I would like to go quickly through one of the Austin examples that it has already been. And this is showing how a transaction, how the blocks in the blockchain are created. And as we can see, this is a pool with all the transactions that are being propagated and the message that are digitally sent. And we have here at the first block that is united to the next block that the miner is trying to find out if all the transactions that are included in the next block are going to be correct. So here in any time, the miner is going to successfully mine a new block. And when we are saying that a block is mined, what we are saying is that the miner did enough computation powers to verify that everything in the list of transactions that he's processing is correct. And once that's the case, we are making sure that all the transactions that have digitally signed a message are correct, so we can include it as the next block in the history. And once that happened, as we can see here, all that transactions are keep it as the first block history. So all these are now part of the blockchain history. And now once the miner are able to identify and as telling again, mine this new block, we are going to be able to include a new list of transactions. So what we just did previously in the example of sending a transaction is send this our transaction in a pool. And of course, this is a local transaction, so that's why the transaction is mined immediately and is included in the history. But in a more real use case, we are going to be waiting a bit in the pool. Our transaction is going to be included in the pool, and after a few seconds or even minutes, if we are not paying enough, the transaction is going to be included in a next block. But miners are all the time trying to resolve computation and trying to find out what are if the next block is correct. And that's that proof of work that is called this process of trying to find out the next block, if is it correct, is I'm sharing a few documentation on that, but it's not that relevant for us, as it's more like a security um, of how the network stays secure, but it's not super relevant for our practical examples that we're gonna be seeing. But I wanted to show anyway how that process happen. And in this case, it's taking a lot of time actually to mine the next block. And but yeah, what eventually will happen is that this block will be able to be included as the history of the next blockchain in the next of the next block. And yeah, that's what I wanted to show in this example. Now, with that in mind, let's continue with the with our example. Let's see. I think okay. I have. Let me see if we can go back to one of the things that we have. Maybe it was this. No. 1 second. Oh no, this is not. Okay, let's start from scratch once again, and let's go quickly through the process of including a mnemonic. We have a mnemonic. We have a text with the key of hard hat. Let's put it once again. Hard hat network. Okay, we want this. And we're going to be using the first one for now. So yeah, we're getting a priority. We want a key pair. And we're going to take this address. So now we have this. Let's also put the balance to make sure we have the blockchain connected here and check the status is right. Okay, we have it here. So we have the blockchain, we have the address. We are getting the correct data. Nice. So now what we would like to do is not only create a new transaction, but in this time, instead of just send value through the network, we would like to actually create a new contract now. So what we will be doing is including a new module called code that allows us to write the code of the contract that we would like to be using. So yeah, what we will be doing here is a really simple contract. So let's say contract hello hi, and let's put it a value here. Maybe we can say a string of public. This is really similar. Greet equal header, and this is gonna be our super simple contract that is gonna be just storing a value of greet that is saying header when it's called. So this is a high-level language called Solidity in this case, and we usually write smart contract code in a high-level language because we don't want to stay at the level of the machine. So what we need to do now is take this contract and convert it into the machine code that is going to be sent into the blockchain. That's the kind of code and the kind of data that the blockchain understands. So the process of doing that is called compilation. And what we're going to be doing for that is introduce this new module called compile. And as we see, the input for this is going to be the Solidity code. That's the one we have here, and the name of the contract. Oh, sorry. So we have also, I'm gonna need the text, the name of the contract. In this case, it's gonna be hi. So what we need now, okay, we have everything, it seems. Okay, we have, okay, we tried to compile now here, and the compilation succeeds. So everything seems fine. If we, for example, forgot to put this, then we're gonna be having a compilation error because Solidity is asking for us to have a semicolon at the end of every line. So yeah, that's why the compilation failed. And as we can see, here is the error that is getting a parsing error. So let's put it back and compile it again. And now the compilation is going to be succeed. And as we can see here, we're going to get in two kinds of data. Let's go ahead and first see what the bytecode means. And to understand, this is what I was mentioning about the machine code that is understood by the blockchain. And of course, we don't know what this means whatsoever. And here, what is interesting to mention is that the part of the Ethereum that understands this is what is called the Ethereum virtual machine. And what that does is process this kind of data and produce certain actions that we can go and see more in detail now. But the Ethereum virtual machine is like the most low-level component of the Ethereum, and is where the different actions that you are writing in a contract in a high level are actually happening. So, for example, here, probably what is the EVM is doing when we are writing something like this is using certain operations to store into a variable this value, no? So all that is happening inside this code in some way. And to have it a bit more of a understanding of this bytecode, we can see it we can go here in Remix. Remix is the other tooling that we are going to be seeing, and it's really interesting to look a bit into prototyping really quick and see what are and deploy and do things with smart contract, but in a really cool environment, developer environment. So here we have a browser to see the contracts we have. Here we have a compilation tab that allows us to configure all the compilation, how it's happening. We have a deploying tab that allows us to deploy and send the transactions to the blockchain and deploy a contract. Debugging tab. And yeah, what I wanted to show really quick here is that if we create a new value with hi, that's all, and we put the same data that we put here. Okay, yeah, this is generated generating the same compilation data here, but in a different structure called artifacts. But if we go and see, maybe here is a bit more convoluted. So let's see in here. We see that we have the compilation happening. We have a few warnings that are not relevant for us, but as we can see here, we have the bytecode as well. And we can copy here and see that this is the object data that we are sending into the transaction. That is the only thing that we are getting in each bill. And as we can see, it's the same, only with 0x at the beginning. And the other things that I wanted to show you is this opcodes. And these are the actual instructions that the EVM, the Ethereum virtual machine, is processing when we are sending this. So this might be a bit maybe too much in details, but it's just an overview because this is something we are not never using actually in practice, but it's interesting to understand how this works and how this actually happening under the hood when we are creating a contract. So the process to go ahead is we write a contract in a high level language. We are compiling it and generating the bytecode. And the bytecode is actually machine code that the EVM, this Ethereum virtual machine, understand and allow and produce all these operations that are happening when we are using the contract per se. So with that, we are going to be leaving this here that is going to be using, and eventually we are going to be seeing also this other parameter that we are going to, but we are going to leave it there for now. And what we will be doing now is creating a new transaction. So let's bring the transaction component once again. Let's put the blockchain as a first parameter. Let's use the private key here. Ouch. And then we are going to be doing a few things here. As we can see, we are also need a to value here, but when we are creating a contract, the to value actually is the address 0. So it will be something like the, sorry, it's going to be something like 0x0000. So 0x000000. This is the address that we are actually using in the to when we are creating a contract, but we can leave it as empty because that's the default address that is used. And when we are, yeah, and that's it. And then value, we are not sending value this time, just creating the contract, so no need to include nothing. And here the data is the one that is important now because we want to include the whole smart contract data as our data value. So we are going to be putting this bytecode as a data. Yeah, sorry. And yeah, that's it. And let's put a ruler. And this, as it is now, is not going to be working yet. And let's see why in a second. So we have this object that is created again with all the data. We're going to be digitally sign this. So let's sign it. And we see the signed data now, in this case, this. And now what we want to do is send the transaction actually to the blockchain. So we have the digitally signed, we have the blockchain. Oh. And finally, we have a button to send the transaction. So we're going to be clicking here, and as we can see, nothing happened, but we can check our network what's happening. No? So we are trying to send a transaction, but we are getting an error because the transaction says that we need at least 6,000 gas, but we only get 23. And that's because the default value, and as we can see in the object here, let's remove this for now. As we can see in the message that we are sending, the gas that we are putting here is 23,000. And to give a bit of context of what the gas is what we are paying the network to process our message or our transaction in this case. So in this case, as we are deploying a whole contract with information and all that, we need to pay more than a usual transfer that is usually cost 21,000. So what we need to do here is input a higher number. So let's try, I don't know, maybe 100, but probably it's not yet there. So we can try again, sign this transaction and send it. And yeah, we are seeing here that now the whole gas is used and is run out of gas. So the transaction is not actually finalizing yet. So let's put it, I don't know, 200,000. And in this case, probably it's going to be working. And we digitally sign again and send the transaction. And as we can see, the hash now is generated and we get a receipt. So the transaction was actually mined and created. So, so yeah, we have now the gas usage was 1,000, whatever. And now we see that the contract was actually deployed and how much gas was used. And we get to see the contract address as well that we're going to be using there later. So yeah, to go a bit into what we just did, from a smart contract code, we were able to, in a high-level language, we were able to compile it and generate a bytecode that is the machine code that the EVM, the Ethereum virtual machine, understand. And that's what we are using as our data to actually deploy the transaction. And now that we have the contract deployed, what we would like to do is interact with it. And yeah, what we finally do is send a transaction and create it into the blockchain. So now this contract is available for us to use and check what is, for example, what's the value of this grid data. And to do that, what we are going to do first is go through what is the next level of abstraction. When we are, as we can see here, when we are interacting with the Ethereum blockchain, we are sending all these messages that are how we interact with the blockchain. And what that's called is a JSON-RPC. It's JSON-RPC protocol, and this protocol is how the Ethereum blockchain and some other protocols interact with each other. And in this case, the Ethereum blockchain is using this JSON-RPC protocol to send message and receive read and write data into the blockchain. My headphones died, and I noticed that, and I noticed that I was speaking, but there was no sound. So yeah, what I was saying about the JSON-RPC is that this is a library, a low-level library that interact with the Ethereum and with the blockchain, the Ethereum nodes, sending messages that are these methods and allow us to read and write information from the blockchain. So these JSON-RPC methods allow us to send transactions, sign transactions, mine a block, get the blocks balance. So let's, for example, see the get a block by number. So if we see, we can interact with this. So let's do that as a test. So let's run the Hardhat console. This is other tooling from Hardhat that allow us to interact with the blockchain in a really easy way. So what we are gonna do here is await network. We are connecting to the network and a provider. So this is gonna be the local host, so in our local computer. We are gonna do provider, that is the actual blockchain, and we're gonna do a request. And this request is gonna have a method that is the JSON-RPC method that we are gonna send, and it's gonna have params. This is an array of parameters that we're gonna send. We're gonna, and to see that, we're gonna be looking into the documentation here and see that the method is called isGetBlockByNumber. So let's put this here, and the parameters are gonna be through to the quantity or tag. This is the number of the block that we want to get, and or we can also say latest, earlier, pending. Let's go with latest. So we're gonna say latest, and then we are gonna also pass a second parameter that is if we want or not the transactions, the whole transactions data, and let's put it false for now. So as we can see now, we are doing sending this message to the blockchain, the is get block number, and we receive that data in the form of the whole information that the block has. And the latest block is the block number 6. We have all this information that is going to be useful in some cases, but yeah, not that important for us now. And the other thing that wanted to showcase in this case is also how a similar information could be retrieved, but with a more high-level library. In this case, we are going to use the high-level library called Ethers that is also configured in this project. And this library doesn't no need to understand a lot about it now, but it's a more an abstraction on top of the JSON-RPC, so allow us to be more user-friendly with the language we are using. So we can say ether provider, and we can say it get block and get the latest, if I remember correctly. And yeah, what this return us is also information about the block, and a lot of that is the same information that we have here. But as we can see, it has a much more, it has already processed some of that, like timestamp, for example. As we can see here, the timestamp was in a really ugly format, and we usually want the timestamp to be just a number. We have, for example, the gas limit and gas use that are usually really big numbers. So we use this is already format as a big number, and that's this big number is also a data type that a type of data that is easier to manipulate when we are dealing with this kind of really big information. So yeah, so what I wanted to show here is that we have, of course, the really complex way to interact that is using a JSON-RPC, and we have all these methods that are available for us to send to the blockchain and interact with it. But usually what we are going to do is just using a high-level language like Ethers that does a lot of the heavy lifting for us and return us much more easy to manipulate data. So yeah, that's the key difference that I want to show. And now, doing that, let's go back to the example that we have it here. And if you remember, we also had this other value that is generated during compilation, and that's called the ABI. And this ABI is an object that is associated to the contract that we just create. And this object is a standard that was also created by and defined to simplify the connection to the contracts in a high-level library. For example, ethers usually want to know what are the ABIs of a contract to talk with it in a more cohesive way. So for example, here, as we can see, we only have a unique value. So the ABI is pretty simple, and we can see that we only have a view function that allows us to access this grid value. And we can see here that the name is grid, the output is going to be a string of type string. So all this, what it does is describe what the contracts that we are connecting are able to offer to us. A function, what are the type of the function, the return type of that function, etc. So that's usually what high-level language like Ethers needs to understand and interact correctly with this smart contract that we are using. So to give a quick example, let's bring a new model called contract, and this is gonna ask us to provide the ABI, the address of the contract, and the blockchain. So let's put the blockchain. Let's put the ABI as well. And as soon as we put the ABI, as you see, this module understands that one of the methods that we can communicate is a greet method. And that's why he's generating this. So now let's look to the contract address that we deploy as we see before. This is a contract address that we create. So let's put it as an input. And let's use it here. So now when we are gonna call this function, that is because the smart contract automatically, the ABI is generating automatically a method, a function here for us to call this greet and get the value of this greet function. So let's call it here, and what we will be getting back when we call it is a value of hider if everything works correctly. So let's do, and yeah, we get hider as a return value. So what is happening here, as we can see here, we are actually using JSON-RPC to do a if call. That is a contract call to this contract from this address and to the address of the contract per se, and retrieving the data. So in this case, the data that is returning is hider. So that's why we are able to get this. So with this is almost everything that I wanted to show you. The final thing is maybe go in Remix and do a more complex contract like this. This is a contract that is in the Solidity examples. So here is a vending machine contract that has that you can later check it out with more detail, but allow us to given an amount of cupcakes, we are able to refill the cupcakes or purchase new from the machine. So let's save this. We are generating the contracts. There are a few warnings that no, but we are getting here the bytecode as we previously see, and we are getting also the ABI. So let's check it. In this case, the ABI is going to be more complex because we are actually having a lot more data, and as we can see here, we have this type constructor that we eventually gonna see more in detail. We have a few functions and yeah, everything else. So yeah, let's remove this. And what I wanted to do now is, now that we have this compiled, let's deploy it also into our. Here we are able to connect to our local network as well with the Web3. So here we are connecting, and we are gonna, as we can see, we have all these addresses available to interact, as we previously see with the mnemonic here. And what we want to do now is deploy this vending machine contract. And as we can see here, we are sending a transaction, and that's deployed to the contract. And here is the actual transaction that was successfully deployed. And as we can see, this contract was much more expensive than the previous one. And in the Remix interface, we can also check what was the transaction information that was used, as we previously did, but in a more easy interface. And we can even debug what was the different steps that happened during the transaction. And yeah, this is a more complex maybe, so you don't probably don't want to do it for now. But what I want to finally show you is that we have now the contract available here to interact. And as we can see, we have all these interfaces already created from the ABI, and we can interact with the purchase function, the refill function. We can check how is the cupcake balance, and here we can see who is the owner of this contract. We are the owners, as we were the one deployed it. So let's, for example, purchase some cupcake, and we need to send some ETH as well. So let's put 25 ETH, for example, and put 25 that we want to purchase 25 cupcakes, and let's do it with other address, for example, this one. So we are sending this transaction, and as we can see, this transaction was correctly, and this is the, sorry, let's see, yeah, purchase was correctly sent. And if we check the address of this and see how is the cupcake balance of this, we're gonna see that it's 25, as was the one that we deployed. So what I want to quickly show is this smart contract that is a bit more complex, and don't feel that maybe it's too much for you, but as a way to showcase how quickly you can prototype something in the remix and try it out really quick, connecting to a local node and see what's happening and if your assumptions are correct. So with that, I would like to finalize this lecture and keep it up during the week with the task and sharing the different questions or answers that we might have. So thanks.